Okay, so good morning, everyone. Good afternoon for some of you. So today we have another webinar from the Pan American Society of Transportation Research, and the topic today is traffic engineering, right? So we have two interesting presentations, around 30 minutes each of one, and um, And first of all, I'd like to say thank you for the two speakers, Professor Rafael and Professor Anna Tsui. And I think I would like to invite the first speaker, Professor Anna. And I have a short description of Anna. Anna Tsui Moreno is a senior research associate in the Travel Behavior Professorship at the Technical University of Munich, which she joined in 2016. She currently is the head of the research group called Travel Analytics, and before this, she was a postdoctoral research at the Universitat Politécnica de Valencia in Spain, where she gained research experience in various transportation fields. She holds a PhD in civil engineering in 2015 from University Politécnica de Valencia. During her doctoral studies, she was a visiting scholar at the University of British Columbia and the University of Florida, and a visiting researcher at the Federal Highway Research Institute. She's a member of the committee called Highway Capacity and Quality of Service of the U.S. Transportation Research Board, TRB, where she chairs the Uninterrupted Flow Subcommittee. And she's also a member of the Traffic Engineering and ITS Committee of PANA. If I'm not wrong, the title's presentation is called Empirical Development of Bicycle Level Traffic Stress Criteria for Rural Highways, right? So Anna, thank you again.
Thank you very much,
If you need
Jose.
something, let's know.
Thank you very much, Jose, for the warm introduction. And then we'll just say, oh, wait a moment. I'm sharing, and then I need to share. Where are you? Here.
You can see your screen.
My
Okay.
slides. Yeah, I'm going to share my slides. And then,
Perfect.
thank you for the warm introduction. And then, gracias todos por participar en esta reunión. Y muchísimas gracias por la invitación. Voy a proceder a hacer mi presentación en inglés. Me la tenía preparada las slides en inglés, pero luego para la parte de discusión la podríamos hacer tanto en español como en inglés. Y gracias por tenerme aquí. And then we're going to talk now and transition to English to the empirical development of bicycle level of traffic stress criteria for the case of rural highways. And I share my presentation here with Yan Xiancai and then also Anna Takayasu, and both of us, the three of us from the Technical University of Munich. And I want to first frame where the framework of this presentation is a follow-up research that we conducted after completing the research project NCHRP 08-135 on the reliability and quality of survey evaluation methods for rural highways. So this project was completed in June 2023, and then the PI was Scott Washburn, which, yeah, the fun fact, he was our host of both Jose and myself when we were in Florida during the research days. And this piece, this NCHRP project was looking at the reliability and also the level of service for automobiles. The bicycle piece was highly qualitative. And then in this project, we conducted a series of surveys. And from there was derived some recommendations of which are the main follow-ups research for the bicycle mode. And one of them is the one that I'm presenting today, is how can we look at the level of traffic stress for bicycles on rural highways. And as introduction, we go back to rural highways, and that's what the US Highway Capacity Manual says a rural highway looks like. So we have an intercity connector, but then also that is intracity connectors or passing roads through scenic areas. The vehicle speed that we're thinking for these roads is between 40 to 55 kilometers per hour for rural town context, or more than 55 kilometers per hour for rural context. So we can imagine that here the predominant use are motor vehicles and then also freight. Still, there's also some potential for recreational cyclists that they want to cycle on rural highways, and also riders that might rely on bicycle as their only transportation mode. So here we're not talking only about leisure cycling, but then also it can be commuters or other purposes that use the bicycle. And here the main question is actually who does cycle on rural highways, and this is in the context of the US. And then also how can we accommodate the bicycle traffic in these type of roads? How it's been done in the past is that we have different design guidelines in the case of the US that were developed to see which are the most suitable conditions for cycling for a specific design user profile. And what I'm bringing here is the FHWA byway selection guideline that for the case of rural context here says how should be the width of the shoulder between 1.2 meters, I think it's 1.4 meters or almost 3 meters, depending on the vehicle speed and also the volume. So the more volume and the more speed, the higher the accommodation should be for the bicycle traffic. And we said that it depends on the target user. And this is a new concept that's been implemented in the US since the last almost 10 years, that is not targeting the entire population, but is targeting a specific user segment. And those segments are based on the comfort level, bicycle skills, or also experience. In the case of the rural highways, we cannot imagine that all the population was there to cycle on a rural highway. So all these design criteria that has been implemented in the past is targeting the most confident groups. In the case of FHWA, is the somewhat confident and also the highly confident. And then if we see the percentages of the population, we're talking about between a 10 to a 16% of the total population that it would be. So it's a niche, I would say. It's not intended for all the cyclists or all the population to cycle on rural highways. And all this distinction based on the level of confidence is following the approach of the level of traffic stress. And this approach started in the 90s with Sorton, and then here he was proposing whether it was adequate or inadequate one facility for a cyclist based on their own perspective. And it gained popularity in the last 10 years after the Mineta Institute. They start creating all these easy lookup tables to create which are the design criteria. And they're basically mainly based on expert opinion. The aim of this approach is to produce a bicycle facility that is compatible with most of the cyclists in order to attract potential cyclists, to increase modal share and then also have more induced demand for cyclists. And it was firstly done for urban areas. So the piece on rural areas is a bit is newer in this sense. As discussed before, it's based mainly on expert opinion, but there's been also some efforts to create validation with urban cyclists of perceptions. But then here, the first question that we wonder is how transferable are these urban conditions to a rural condition, which might not be the case because of the high speed differentials between the bicycles and the car traffic. Then when we go here to the rural time context, we already seen that there's a higher bikeway accommodation when we increase the speed and volume. And in the case of the US, there's some guidelines being created here, for example, Oregon DOT, Minnesota, and then also Colorado DOT. They have their own LTS-based design guidelines, also AASHTO and FHWA. But when we look at the values that they're proposing, they have a really broad variation of the thresholds. So here's just one example. When we took a daily volume of 7,000 vehicles per day and then 40 miles per hour speed limit, they change between 0 and 8 feet, the shoulder width that is required. So we're talking between 0 and 2.4 meters, which is a wide variation. And there's also some experimentation that it can be changed. Basically, we have rumble strips, or we have more vehicles, heavy vehicles, or there's debris on the pavement. It can increase the stress level. But so far, all these design guidebooks were based on expert opinion. So here will be the main question is, how can we validate these design criteria, not only based on expert opinion, but with user perceptions? And this is what it brings us today as our objective will be to develop this framework to derive the design criteria on rural highways based on empirical data. And to achieve this aim, we have a series of subsequent objectives. The first, it will be to design the survey in order to know and gather which are the variables that the people have an influence on their decision to cycle or not. And then also distribute this survey to collect the opinions for actual cyclists, and also which are their attributes and characteristics. From there, estimate individual preferences, and lastly, develop these recommendations for here the case of level of traffic stress based on user perception. And to the best of our knowledge, this will be the first attempt to derive the design criteria based on user perception and empirical data. The methodology that we follow. So as usual, we started with a really large lead review, and then here is just a snippet on how the different methods have been used in the past. So we start with a level of service that is closer to the highway capacity manual. It started in the 80s in the Netherlands, but then it's been more research done throughout the years. And later also happened the level of traffic stress was introduced in the 90s. And what we can see is that there's a lot of research after 2012, when it was the first published from Mercuria et al. And also the Bakeability Index. What we can see actually is that all these methods have been developed concurrent on time, and then it's not an official position whether to use a level of service, level of traffic stress. So it's a lot of debate on which one to use and which one is more appropriate, because all of them have been, as I said, developed concurrently on time. So when we deal more with the design studies, and here is a list of the different design guidelines that have been done based on the level of traffic stress. What we see in bold are the ones who relate to rural highways. So there are not that many. Most of them are for the urban area, and usually also these ones that are in the rural area also have the urban counterpart. So the rural area has been less studied, and as you can see here, they're based on lead reviews and expert opinion. So there's not much empirical analysis for LTS-based design guidelines. So with all these P's, we created a first practitioner survey. So this was targeting individuals who have expertise on designing or operating bicycle modes on rural highways. And here we were asking them which were the different, how is this parameter affecting the perception of the quality of service for a user? So here is based on the expert opinion. We're thinking how you think that a user will evaluate this aspect for their quality of service. And what we saw is that there's differences depending on shared lanes or bike lanes, but the attributes that came more into our analysis were related to the speed limit, volumes, and then also the clearance, which is the separation between the bicycle and then also the automobiles. And based on the practitioner survey, we developed our user survey. That's the one that I'm going to talk about today, because here we talk about empirical data with the user perceptions. And then this survey, as I say here, was in this NCHRP project with our partners for the project. It's a stated preference survey that was conducted online, and the main objective was to identify the variables that are relevant for a person to decide to cycle or not on a rural highway. And here has different pieces of the preference survey, and what I want to talk more today about are the choice experiments that they were developed. The survey was pre-tested with the team and also project partner members, and had the approval for the University of Florida IRB. And after that, it was distributed online to Cyclist Association, also social media, UTCs, and the different state DOT, bike ped coordinators, and different committees at TRB, because our sample target was in the US. And with this, we dwell now on what are the choice experiments that we had. And the choice experiments, what we can see here on the right-hand side are the instructions given to the people. And we were telling them you will have 4 questions, and for each question, you will need to imagine that you're riding your bicycle on a rural road, and which of these cycling conditions serves you better your needs as a cyclist. And then here they have to choose one of them. If they feel like none of them is comfortable for them, they can also opt for none of them. And this is a single choice, so they can only choose one of them. How we got here, we started identifying rural routes in the US with high bicycle use, using Strava and also Mapillary. And we were extracting their attributes using OpenStreetMap. That piece, together with the practitioner survey and the review, let us identify 6 attributes that they were the most relevant for our experiment. And you can see them here faster than I will read them. But yeah, we have 6 attributes to be playing with, combinations for our choice set, and they have between 2 to 3 attribute levels. If we start doing all the combinations of all these 6 attributes with their 2 or 3 levels, we end up with 324 alternatives. And it's something that's not bearable for a participant to analyze each one of them. So we use fractional design to reduce the choice task dimension from 324 alternatives to 16 representative alternatives. And these are the ones that you can see here on the slide. So they vary the content class between rural town or suburban, a speed limit low or high, the grade or terrain, the presence of a shoulder, automobile volume, and pavement conditions. So these were the description of the different scenarios, but instead of showing each person a description, we show them a picture. And how we created the picture was retrieving video images and then from Mapillary to create those hypothetical scenarios. And then here is using streets or highways from the US. And then to them, we edited the speed limit signs, automobile volumes, and also pavement conditions. And here we have the example of 2 of these choice sets, and one would be the image number 4 that had a narrow shoulder, little low traffic volume, a high speed limit, pavement is acceptable, and the terrain is level. And then on the other one, you can read them faster, that will read them. So here we can see the differences that were edited to the people. So once we created these 16 scenarios, we implemented all of them in our Lime survey analysis, and we divided those scenarios in 4 groups of 4 choice tags. So each choice tag had 4 alternatives to the persons, and then how they created those groups or choice sets, it was randomly. So for each person, they will have a different order and a different arrangement of the choice set, but each person was able to see all the 16. So that was ensured in our code. In order to increase the sample size, we did the choice sets twice. So each person had to do 8 choice sets in total. And for the modeling framework, and here comes the specific improvement compared to the NCHRP project that we were working with, is that instead of using multinomial logic or nested logic, we went to mixed logic model. And then in this case, the mixed logic model used a distribution of the taste parameters that for the design attributes or over the entire population. And that distribution was assumed to be normally distributed. So instead of having just one for each segment of the population, we have an entire distribution of the taste parameters. So they were at the individual level. It was estimated using Markov chains, Monte Carlo methods in BioGym, and this is useful when we have these multivariate distributions that are unknown. Specifically, we'll able later to evaluate individual level taste parameters. So there was after we have the estimation of the mixed logic model, we have all these distribution taste parameters, and using simulations, we were able to derive their individual beta value for each one of the parameters for each one of the persons. And this methodology was previously used by Henser to evaluate the willingness to pay estimates for each person individually. Now we're getting to the fun part, will be the results and discussion. So, which was our sample size? It was almost 1,000 complete responses with the distributions that you could see here on the screen. We have more males than females. Also, the income levels were on the high side. And when we look at the confidence level, because we asked the persons, how would you identify best yourself? How will you describe best your confidence level? And most of them, they said enthused and confident and also strong and fearless. So we have almost 80% of our sample were on the confidence side, which is actually the target user on these design guidelines. Still, we also have a 20% of the respondents who were less confident, and that we can say that they might rely on bicycle for transportation. So, but they would be cycling on a rural highway. And this distribution seems plausible for individuals cycling on rural highways, based also on previous literature. We estimated the model, and then here we have all the coefficients, and what we can see here are the mean values and the standard deviation for the different attributes. And how to read this table is, because it's a discrete change model, we always compare the likelihood towards the reference value. So for example, here we can see the shoulder, no reference, and then we have coefficient for narrow shoulder and wide shoulder. The larger the coefficient, the larger this mean value, the more difference between not having the shoulder and having a wide shoulder. And here we see that it's 4.7 almost, the mean value, that when we translate that into the odd ratio, this means that it's 17 times more likely to select a scenario with a wide shoulder compared to a scenario without shoulder. And this is how we can read this value. So the presence of shoulder, as we can see, based on the mean value of our coefficients, has the most significant positive impact on the utility. So the most driving factor for selecting to this scenario for riding. And then this is followed by good pavement conditions, and then also having a narrow shoulder compared to no shoulder. When we look at these values, they align with the bicycle safety performance function for road segments that they were developed in another NCHRP project for the US. So we are confident that our results go in the appropriate direction. And then after looking at these mean values, I'm going to have the representation of these values, which will be easier to grasp. And what we're seeing here is the distribution of the individual preferences of these attributes. So after we calculate the mean value and their standard deviation, we use simulation to provide a beta to each one of the persons in our sample. And here are how the betas are distributed across the sample that we had. What we can see is that most of them, they have a bell shape. So the assumption of the normal distribution is holds for most of the attributes. Only when there's a narrow shoulder, we have these two peaks present. That here what it implies is that for some participants, having a narrow shoulder, it was worse than actually not having a shoulder. But all others function as we might expect. So when we have a wide shoulder, it increases the likelihood. The pavement good also increases the likelihood. And when we have higher volumes, we have negative betas. So higher volumes will decrease the likelihood of being selected. And this analysis is done now at the aggregate level. So for each one of the individuals, we have their betas and it's calculated at different distributions. But because we also know which are the social demographics and also their cyclades confidence levels from our population, we could segment this analysis by any of the attributes of interest. And the first one that we had was this confidence level that the people were saying. And it comes to my next slide, where we were looking at the distribution of the betas based on the confidence level. So here is the same graph as before, that the dark color is the average person that we will have the entire distribution. And then by colors, we have a different confidence level. So being the pink, interest by concern, less confident, and then the purple, strong and fearless, the most confident. What we can observe is the first one, when we look at the traffic volume, all of them, they kind of overlap. So we cannot see significant variation across the different cyclist types in the case of low traffic volume. And then if we look at the speed limit high, we can see that the pink one is a bit different than the other two. So we can say that the impact of high speed limit does not change for the most two confident groups, but it only affects the one that is less confident. So which is also important to see that for them, it doesn't make a difference. When we look at the most confident group, also they has a unique distinction distribution for the high traffic volume, suburban context, and wide shoulders, which also makes sense because then if you are the most confident, you will have a different, the likelihood of cycling when you have a wide shoulder might be smaller than the effect that will produce for the least confident groups. So, and then in this case, both interest by concern and also enthused and confident, they have a similar taste for the shoulder weight. And we also saw another ones that all of them differ. So we can see that there is no a clear trend that two of them overlap, but all of them are different, but they follow an expected pattern. So when we have good pavement, the ones that have a higher effect on them will be the least confidence compared to the most confidence. So all of these make sense, but we can see that there's no a trend that is unique across all of the different attributes. And then here, what it comes to say is that the self-stated confidence level fails to capture this systematic variability. So if we will have a unique mean value for everyone who is in one confidence group, we will not be able to see these differences because for some cases they overlap two groups, for other cases they do not overlap. So this approach produces more accurate results than having the unique value for each segment class. And after looking at each one of the individual values and betas, we calculated the propensity to cycle. So here is how is the probability of a person to choose to cycle on a specific combination scenario with all the attributes. And then this can be used if we want to do sensitivity analysis, if we start varying certain attribute levels. And we use it here, for example, for the context class, that we can see the first thing is the difference by shoulder is the one that gives the most different shapes of all these propensities to cycle, meaning that the wider the shoulder, then the differences for different context class are minimized. So we can see that the three lines get closer to each other. When in the other case, when we have no shoulder and we are in a suburban area, it's much more likely that you will choose to cycle. But in a rural area or in a rural town, people will not dare to cycle there because then the propensity to cycle is pretty low on that scenario. And we can have similar analysis for other attributes. Here we can see with the pavement condition that is fixed, also the rural class fixed, and the level terrain. We can see which is the impact of playing with the high speed limit and also traffic volume, and also the shoulder width. As we saw before, the presence of the shoulder and its width is the one that changes more dramatically the shapes of the propensity to cycle, and the differences across the traffic volumes they're minimized when we have no shoulder and high speed. So regardless which is the traffic volume, we will have, in all the cases, really low propensity to cycle. Then that's different when we have a wide shoulder and a low speed limit, then we will also see differences. So the higher the traffic volume, the least propensity to cycle. There are similar analysis could be done with the pavement conditions. That here is quite interesting. When we have a wide shoulder, it's only different when we have a good pavement condition, but when they're either acceptable or deteriorated, it doesn't make a difference for wide shoulders. But then when we have narrower shoulders, then we can see these differences across the pavement conditions. And something that was interesting for us was the terrain, because our main assumption was that if we have a rolling terrain, so we have more grades up and down, people would select to cycle less, because usually you tend to minimize your effort and you will select that. But we found the opposite. So we found that when we was rolling terrain, people were more prone to cycle. And that could be also because people might have not thinking on terrain as this utility or more effort to cycle there, but it could also be that it was fun, or also that it was shaded because it was desert-like when it was level terrain, and the others were with more trees around. And here comes the application. So because I was talking about which is the model results and then also which are the different sensitivities, how can we actually apply this to derive the level of traffic stress criteria that I mentioned at the beginning of the presentation? And how to apply it is that we can start calculating different propensities to cycle based on combination of the attributes. So here, for example, we have one combination of attributes that it was our image 10, and we can decide like cycle is recommended for all if most of the people have a high propensity to cycle. So if a lot of people, in this case, the first quantile means that 75% of the people will have at least a probability of 75% to say, yes, I will cycle here. So under those conditions, we can, and then these thresholds can be set, anchor points can be set by each one of the users, but then this could be one example of this could be acceptable for everyone. When we're looking at only for advanced and confident users, we're talking here about the Q3, which will be the top 25%. So the 25% of our sample that are the most confident, that at least they have to have a 50% chances of selecting here to cycle. And this is one value that we can recommend. But then if this top 25%, they don't dare to cycle, so it's their propensity to cycle is between 25 and 50%, we say is not recommended cycling here, and this will be one of the examples. But if it doesn't even reach the 25%, we can say this is not suitable. Not even the most confident cyclists will dare to cycle. So we can classify this as non-suitable, and we need to have a shared use path if cycling is going to happen here. And based on this, we look at our choice set images, and then we start proposing different recommendations to them. And what is more interesting than this would be how they change also the design criteria that was proposed by others. And here we have a list of the different recommendations from the beginning that I mentioned with FHWA, Oregon DOT, AASHTO, and then also Minnesota DOT. What we can see just from this slide is that in the case of Oregon DOT is the one which one is more less conservative values because it allows cycling in most of the conditions. The most restrictive will be FHWA. As we can see, a lot of these conditions is not suitable for cycling. And for each one of these, we calculated the propensity to cycle, and we apply our criteria. And from using our criteria and our anchoring points, we were able to also define a set of when it's likely for cycling or not. And what we can see is that our analysis results, they align quite well with AASHTO. And in most of them, we have a coincidence whether it's allowed for cycling for advanced users or for all. We only have, in the case of rural time, we have a less conservative criteria. According to our results, the propensity to cycle is quite high. So we will recommend in this one to cycle for all the users compared to the AASHTO that is only for advanced cyclists. And in the case of narrow rural roads with high volume or narrow shoulders with low volume and high speed, we will have more conservative criteria than AASHTO. But everything else is quite similar to what AASHTO was proposing. And with this, I will come to the conclusions of today. So first, here was created a robust approach with empirical derivation of the recommendations for bicycle facilities in the rural context that is based on empirical data. So here we were targeting almost 1,000 respondents from the US, and this sample was aligning with what is the target user groups for this context, but also included a 20% of the sample that can rely on bicycling for transportation. The approach that we developed uses the entire distribution of these parameters. So instead of the previous ones that depend on a segmentation for individual attributes and therefore are subject of bias or self-reporting, here we were producing individual variables, individual values for each one of our respondents. And compared to the previous guidelines, they were close related to what AASHTO is proposing. The main conclusions is that our propensity to cycle is really sensitive to shoulder width, speed limit, and traffic volume, which is not surprising, although guidelines use these three elements. But also we have found a moderate sensitivity to pavement, terrain, and context class. What we also saw is that there's some intra and inconsistencies on the individual taste parameters by cyclist type. So using percentiles of the distribution might be more representative than using a pre-segmented distribution of the self-stated confidence level. And with this approach, we were able to derive the recommendations and all these anchoring points, and here I show which could be our proposal, could be set flexible by each one of the agencies if they want to have more conservative or less conservative criteria. There's some limitations to our research, so it's limited to the choice task design that we had, and then we're using still images, not video or other type of images that could be producing different effects to the people. Our limited sample, still it was almost 1,000 respondents, but it could be larger. And it can also have some biases into the most confident groups. It can be some interpretation bias that we saw based on the images that people might be interpreting a different thing than what we were implying. And also this modeling framework has an assumption that it was hold for most of the attribute, but one was not. And as future work, we would like to continue exploring, which is the role of the bicycle segment users for rural highways, also increase the sample size, and then that will improve even better our model estimation results, and also do the expansion to other urban areas and also to other countries, because it will be really interesting to see if these taste distribution parameters hold in the US compared to Europe or compared to South America. And then the last piece will be to discuss these anchoring points, because then this is our assumption that we defined this Q1, Q3, and the 75%, etc. But it will be open for discussion to do that with other practitioners. And I think that's the end of my voice and also the end of my presentation. So thank you very much for your attention, and I will be open for any question. And as I said before, in either Spanish or English, we can have that.
Okay, Anna, thank you very much for your presentation. Maybe it's better to move to the next presentation, and then at the end of the Rafael's presentation, we can move to the question discussion. So I'd like to invite the audience to write on chat, and of course it's possible to raise your hand to make your questions after Rafael's presentation. Okay. So I'd like to invite Rafael to present your work. I have a short description here. Rafael Dopian is an assistant professor at the Universidad de los Andes in Chile, and he holds a PhD in transportation engineer from the Pontifical Catholic University of Chile. And his research focuses on traffic flow theory and intelligent transportation systems. Thank you very much, Rafael, for accepting our invitation. Yeah, please.
Thank you, Elievan, and thank you everyone, the organizers in the first place, and everyone else attending to this presentation. I took the liberty to present in Spanish, so I feel for those who don't speak Spanish, but I'll do my best to speak slowly and as well pronounced as possible, despite of my Spanish, my Chilean Spanish accent, which is itself difficult. Ok, entonces voy a hablar hoy día de la, se ve la presentación, ¿verdad? Voy a hablar hoy día de la influencia de distintos parámetros geométricos del diseño de curvas horizontales en el desplazamiento lateral de los vehículos. Este trabajo lo vengo haciendo hace algún tiempo con ayuda de estudiantes de pregrado que hacen su tesis de salida de la carrera de ingeniería, y con Tomás Echaveguren, profesor de la Universidad de Concepción, a quienes algunos de ustedes pueden conocer. Hoy día, entonces, voy a hablar primero de la motivación de este trabajo, cuál es mi pregunta de investigación, cuál es la metodología aplicada, para luego pasar a los resultados y, finalmente, algunos comentarios, ideas de investigación futura, y etcétera. 5 puntos. Y entonces, en primer lugar, ¿cuál es la motivación? Los primeros accidentes de los vehículos autónomos de Waymo, que no eran fácilmente atribuibles a un ser humano, porque el computador estaba apagado, porque digamos, estaba en modo de conducción manual, o porque fue un choque por atrás de un tercero. Las primeras colisiones que no eran atribuibles fácilmente a un ser humano, sino que había sospecha de que eran causadas por el robot, por el conductor autónomo, fueron colisiones laterales. Y es que en el mundo de la conducción autónoma la dimensión lateral se ha estudiado poco. Parte también de la motivación tiene que ver con los Tesla. Una queja común entre los usuarios de Tesla al adelantar vehículos pesados, camiones, buses, es que los adelantan muy cerca. Y es que inconscientemente el ser humano tiende a tomar distancia cuando adelanta un camión. Y el conductor autónomo está más preocupado de mantenerse centrado en la pista. Esto ha ido evolucionando con el tiempo, pero es una cosa que también pasa en el mundo real de los vehículos autónomos. Otro punto de motivación tiene que ver con el pavimento. El pavimento de las autopistas y carreteras se diseña pensando en cómo va distribuida la carga de los neumáticos en la posición lateral. ¿Qué tan probable es que un punto en particular de la carretera a lo ancho sea exigido por el peso del auto transmitido a través de los neumáticos? El problema es que los neumáticos no siempre están donde mismo, y entonces es como una variable aleatoria que se distribuye. Incluso hay autos que son más anchos, y entonces finalmente lo que tenemos no es un punto exacto donde los neumáticos ejercen el peso, sino que es una distribución. Y de la densidad máxima de esa distribución se sacan conclusiones sobre cuál tiene que ser la resistencia del pavimento. El problema es que este diseño se hace igual en rectas que en curvas, y hay razones de más para pensar, que esas distribuciones son distintas, que en una curva pasan algunas cosas, los conductores tienden a irse hacia el centro de curvatura, y por lo tanto esas distribuciones podrían cambiar. En este contexto, entonces, la pregunta de investigación es, bien, en las curvas, ¿cómo afecta la geometría de una curva más o menos cerrada, a la elección de la posición lateral y particularmente a lo que se conoce como wandering, que es la distribución y el desplazamiento lateral de los vehículos a medida que conducen por la infraestructura, en este caso por una curva? Un pequeño paréntesis sobre geometría de curvas. Aquí tenemos un ejemplo de una curva general de diseño moderno. Voy a poner el puntero láser. Y se distingue entre la recta de entrada y la recta de salida. Se distinguen 3 segmentos. El primero se llama la transición, podríamos llamar la transición de entrada, que corresponde a una curva que se llama clotoide generalmente, o también se conoce como espiral de Euler, que tiene la gracia de que su curvatura crece linealmente desde 0 hasta llegar a la curvatura de régimen del siguiente segmento de la curva. El siguiente segmento de la curva es propiamente un arco de circunferencia. Finalmente, el tercer segmento de la curva es una clotoide o espiral de Euler en el sentido contrario, es decir, que va desde la curvatura igual al arco de circunferencia hasta curvatura igual a 0 y continuidad con una recta. De esta manera, esto viene de la época de los primeros trenes, las primeras curvas en líneas ferroviarias eran simplemente arcos de circunferencia, y cuando los ferrocarriles empezaron a andar a mayor velocidad, se empezaron a descarrilar. Y la solución, entre otras cosas, que algunos aquí conocerán mejor que yo, la solución fue crear estas curvas de transición donde la curvatura va creciendo gradualmente. Y entonces, entre los parámetros de la geometría de curvas que nos interesan, está, bueno, los parámetros que podríamos decir horizontales, que todos conocen, como el peralte y la pendiente. El peralte, ¿verdad?, es esa pendiente lateral, transversal a la vía, que ayuda a contrarrestar el efecto centrífugo de la curva cuando un vehículo anda en línea recta, la enfrenta en línea recta. La pendiente es la pendiente que enfrenta el vehículo mismo, si va subiendo o bajando el camino. Después entramos ya en elementos de la geometría de la curva horizontal. El radio de curvatura es quizá el parámetro más fundamental. Después hay que mencionar el ángulo de deflexión, que es cuánto dobla desde una recta hasta la otra recta, qué ángulo hacen las dos rectas, o podríamos decir en lenguaje coloquial, cuánto dobla un vehículo a raíz de esta curva. Y en tercer lugar, de los parámetros de las curvas horizontales, en quinto lugar de todos estos parámetros que estoy mencionando, es la longitud de las transiciones. Solo con estos 3 parámetros, el radio de curvatura, el ángulo de deflexión y la longitud de las transiciones, que podrían ser 2 parámetros si la curva es asimétrica, tiene las transiciones de distintas longitudes. Con estos parámetros se puede definir cualquier curva en el plano. Uno agrega la pendiente y podría ser un poco más detallista y agregar todo el perfil vertical, ¿verdad? Uno agrega la pendiente y el peralte y ya tiene prácticamente cualquier curva de diseño. Sigo entonces con la metodología. Esto fue con ayuda de un alumno de pregrado que revisó más de 100 curvas en distintos lugares de Santiago. Aquí tenemos a la izquierda un extracto del mapa de la zona central de Chile. Se ve que buscó muchas curvas alrededor de Santiago, también en algunos caminos de montaña cercanos y en distintas zonas suburbanas digamos, 100, 150 kilómetros alrededor de Santiago. Finalmente, de esas curvas se eligieron 8 Aquí solo se ven 6 porque en este lugar hay 2 que están muy cerca una de la otra y en este lugar hay 2 que están muy cerca una de la otra. Hubo un primer trabajo en que solo se analizaron 2 curvas. La idea era que hubiera una curva de radio grande y una curva de radio pequeño, una curva de ángulo de deflexión grande y una curva de ángulo de deflexión pequeña, una curva con transiciones cortas, o sea, casi circular, y una curva de transiciones largas. Y entonces con esas 2 curvas en mente nos pusimos a buscar otras que completaran una especie de diseño de experimentos que combinaran estos 2 niveles de radio de curvatura pequeño y grande, ángulo de flexión pequeño y grande, transiciones largas y cortas, y finalmente convergimos a estas 8 curvas que resultaron no ser perfectas para el diseño de experimentos, pero de todas maneras permitieron después hacer una regresión lineal. 3 de estas curvas son en caminos de montaña, poco transitados, que se adentran en la cordillera de los Andes, una en una autopista urbana, en un lugar que es difícil llamar urbano porque es un cerro que está despoblado, el Cerro San Cristóbal, un parque urbano que está dentro de la ciudad. De hecho, la autopista es una autopista urbana que une dos lugares distintos de Santiago, pero justo en ese lugar está rodeada de campo, de descampado, y 4 en autopistas interurbanas saliendo de Santiago hacia el sur y hacia el norte. Con eso obtuvimos ángulos de deflexión que iban desde 41 a 68 grados sexagesimales, radios de curvatura entre 59 y 410 metros, y transiciones también variadas que no voy a detallar aquí, pero sí, una curva que casi no tenía transición, una curva muy antigua que casi no tenía transición, algunas que eran casi únicamente transición sin segmento circular. Y entonces la metodología, no quiero aburrir con este slide, pero la metodología, el panorama de la metodología es grabar y sacar fotos mediante un dron verticalmente desde arriba de la curva, en video cenital, y fotos georreferenciadas, y entonces el video se procesa, se extraen mediante el software Data from Sky, se extraen las trayectorias primero en coordenadas del video, y después se traduce eso a coordenadas geográficas. Para mayor precisión de las coordenadas geográficas, mediante las fotos georreferenciadas se construye una maqueta 3D mediante un software de reconstrucción 3D que alimenta la calibración de la traducción de coordenadas del video a coordenadas geográficas. De la misma maqueta 3D se extraen las curvas. Aquí manualmente hubo un trabajo de otro estudiante que fue marcando en la maqueta punto por punto, cada aproximadamente 1 metro, cada una de las líneas de pista y de las líneas de los bordes del camino, de cada una de las 8 curvas. Y bueno, después hubo un proceso de cálculo de los parámetros de las curvas a partir de esa extracción, y después mediante un programa de desarrollo propio se calcularon las trayectorias relativas, la posición lateral en particular, que era lo que más nos importaba, relativas a la vía, y para terminar calculando métricas de este desplazamiento lateral. Y con eso para muchos vehículos, vamos a ver que tuvimos cerca de 1000 trayectorias, hacer regresiones lineales respecto de la geometría. Y entonces decía, el primer paso de la metodología es la filmación. Estos son aproximadamente los drones, de hecho no son exactamente los mismos modelos, pero se ven muy parecidos, que usamos, un Autel Evo 2 y un Phantom 4 de DJI. Luego fuimos a los distintos lugares y tomamos videos. Los videos que finalmente utilizamos eran segmentos cortos de 4 minutos, excepto por los caminos de montaña que tenían poco flujo, y por lo tanto ahí tomamos 15 minutos para tener un tamaño muestral un poco mayor. Esto es lo que yo decía, tenemos la reconstrucción de la maqueta 3D. Aquí se ve una foto aérea con las curvas de nivel sobrepuestas. Se ven curvas de nivel incluso para la vegetación. Este es un software muy preciso en lo que hace a partir de las fotos para reconstruir la maqueta 3D, y en rojo están las líneas, esto probablemente se vea un poco pixelado, pero en rojo están las líneas que fue marcando manualmente el alumno. A continuación tenemos la calibración hecha por nosotros mismos. Se ven como puntos de colores los puntos capturados por el alumno, y se ve como la línea azul superpuesta, la curva de transición de geometría ideal, es decir, con exactamente una clotoide, un arco de circunferencia y una clotoide, que mejor se aproximaba a estos puntos que se indicaron sobre la maqueta. Esto mediante un proceso de optimización cuya función objetiva era la raíz del error cuadrático medio entre de la distancia de cada uno de los puntos a la línea resultante. Y en general se obtuvo para cada línea menos de 10 centímetros de error, que era más o menos la resolución que teníamos en los videos más grandes. A continuación, y entonces aquí simplemente un detalle, si hacemos zoom a esta parte de acá, se ve que el fit no es perfecto, y aquí elegí un caso en que particularmente no fuera muy perfecto. Aquí hay una parte de la línea que los puntos son la línea dibujada en la calle, ¿verdad? Extraída de la maqueta, y se ve que se desvían un poco de la línea, pero hay otros lugares en que los puntos van perfectamente alineados. Y esto se puede deber a problemas de implementación, a problemas de la perspectiva, que no es perfecta porque es un video desde arriba y lo que están filmando, el plano de la vía, en realidad no es un plano. Puede haber distintos motivos, por lo que los 10 centímetros de error en verdad parece poco, y por lo menos a nuestro criterio resultó aceptable. Luego viene la extracción de la trayectoria mediante data from sky. Aquí tengo un ejemplo de la trayectoria de un auto en una de estas curvas, en azul, y entonces calculamos la distancia más corta entre cada punto de la trayectoria y la línea calibrada, la línea ideal de pista, de borde del carril, que le corresponde. En este caso se trata de un camino de montaña de un carril por sentido, y entonces la línea que le corresponde a este auto es la línea más interior de su sentido, y entonces ahí vemos como a medida que se acerca al vértice de la curva, se aproxima hacia el centro de curvatura y luego vuelve a alejarse. Y en base a eso automatizado para todas las trayectorias, obtuvimos las trayectorias ahora calculadas relativas a la vía. Y entonces aquí tenemos el 0, es la posición lateral correspondiente a la línea que limita el carril. 1 significa 1 metro de distancia de esa línea, 2 significa 2 metros de distancia de esa línea, y aquí tenemos el ejemplo de la misma, creo que es la misma, no es la misma, pero es una trayectoria de este mismo camino, que parte a una cierta distancia, cercana a 2 metros, a medida que avanza, se va acercando al centro de curvatura, llega un momento antes del vértice en que alcanza su distancia mínima y luego empieza a alejarse de nuevo para terminar la curva muy cerca de donde la empezó. Bien, y entonces la métrica que calculamos fue el máximo menos el mínimo. O sea, en el fondo, ¿cuál fue el span completo de posiciones laterales que ocupó este vehículo a lo largo de la curva? No necesariamente el máximo, esto es casualidad, no necesariamente el máximo ocurre al momento de empezar la curva, y el mínimo sí se puso como requisito que tenía que ocurrir en el segmento de curva circular. Y entonces el promedio entre estos dos se considera como el máximo. Con eso también se corrigen problemas de la calibración de la curva o incluso de la perspectiva del video, y eso menos este mínimo se consideró como lo que llamamos wandering total. nuestra variable dependiente para las regresiones lineales. Entonces extrajimos el wandering total de cada trayectoria. También extrajimos otras métricas, pero esta fue la que resultó mejor explicada por los modelos. Por eso no me voy a detener en explicar las demás. Y variables independientes incluimos, bueno, supongo que muchos de los que están escuchando se podrán suponer algunas, el radio de curvatura, el ángulo de deflexión, al que llamamos teta,
Ya tu
las
permanencia
longitudes,
definitiva aquí.
las longitudes de las transiciones, de entrada y de salida. Por generalidad preferimos considerarlas distintas, aunque en teoría, por norma, en Chile debieran ser iguales, en la práctica no siempre son iguales. El sentido de la curva, en toda curva bidireccional, los que están más cerca del centro de curvatura van a ir doblando hacia la derecha, y los que están más lejos del centro de curvatura van a ir doblando hacia su izquierda. La única excepción a esto es la autopista urbana, que es en un solo sentido, porque el otro sentido va bajo tierra. Y entonces el sentido de la curva, el ancho de carril, el número de carril, contando desde más cerca del centro de curvatura hacia más lejos, 1, 2 y 3, como variable entera, el peralte medido en pendiente percentil, la pendiente también medida en porcentaje, metros subidos cada 100 metros de avance, la velocidad de cada vehículo, la desviación estándar de la velocidad de la misma trayectoria del vehículo como una medida de si cambió o no de velocidad durante el desarrollo de la curva. Y después fuimos agregando otras variables para sacar, para incluir más información y eliminar variables correlacionadas. Por ejemplo, la velocidad relativa a la media del sitio. Recordemos que son 8 curvas a cada uno de estos escenarios, de estas curvas, y a su respectivo video y a las trayectorias extraídas del video le llamamos sitio. Y finalmente, el sitio. Ya voy a explicar por qué esto fue importante, pero dejamos una variable categórica para definir cada uno de los 8 sitios. Pasamos entonces ahora a los resultados. Estos son los 8 lugares. Si quieren, después me puedo detener en cada uno de ellos. Y encontramos en cada uno de los escenarios desde 19 hasta 230 casi vehículos, trayectorias. Curiosamente, esta es la que yo decía, la autopista urbana, y es la que tiene más flujo, no es casualidad. Número total de carriles considerados, ahí están los caminos de montaña que tienen un carril por sentido, y por lo tanto 2 carriles en total, hasta una carretera interurbana que por su pendiente tiene, en uno de los 2 sentidos, tiene una tercera pista para los vehículos lentos. Y tenemos, muestro aquí nada más un adelanto de que se ve que hay distintos valores para el promedio del wandering total de todos los vehículos observados. Otro ejemplo anecdótico, aquí tenemos la Cuesta de las Chilcas, que es esta carretera que tiene mucha pendiente y que por lo tanto tiene 3 carriles, y ahí se alcanzan a ver, espero que se alcancen a ver, las trayectorias individuales de los vehículos que van por la ramal interior, o sea, doblando hacia su derecha, y los que van por la ramal exterior, o sea, doblando hacia la izquierda. Esto es parte del procesamiento. Aquí vemos esta misma curva de las Chilcas Norte, y vemos cada una, en un color distinto, cada una de las trayectorias individuales en sus coordenadas relativas, coordenadas laterales en este eje, relativas a la línea más interior, y en este eje tenemos la distancia recorrida en la curva. Aquí tenemos una curva que en total, desde que comienza hasta que termina, son aproximadamente 500 metros, y que tiene, en un sentido, tiene una clotoide de entrada muy cortita y una clotoide de salida más grande. Este es el que yo decía al principio, este es un camino histórico, que está en quizá uno de los lugares más difíciles de la Ruta 5 Norte, que es nuestro segmento de la carretera panamericana, cercano a Santiago, que está entre medio de cerros, y entonces no tiene muchas más alternativas de por dónde ir, y no hay mucho espacio, y entonces está la geometría de la curva, y el cuánta clotoide se puede o no se puede hacer, está en buena parte limitado por por la geografía. Y entonces aquí vemos aquí una línea horizontal sería un vehículo que no cambia su posición lateral en todo el trayecto. Vemos algunos vehículos que cambian de carril en la mitad del proceso, aquí otros vehículos que cambian de carril, y después vemos en cada uno de los carriles un grueso de vehículos que siguen este patrón de que parten alejados del centro de curvatura, se acercan y finalmente se vuelven a alejar. Y aquí se ven claramente las trayectorias de los 3 carriles que van hacia el sur, hacia Santiago en este caso, y los otros 2 carriles que se alejan. Yendo ya a las regresiones lineales, una cosa que llama la atención, tenemos un R cuadrado del prácticamente el 60%, pero una cosa que llama la atención es que las variables categóricas correspondientes a los sitios, la pirámide, la ermita, el tollo, aparecen como altamente significativas. Lo que lleva a pensar que hay algo en los sitios que no está capturado en la geometría, que puede ser la visibilidad, puede haber sido la temperatura o la hora del día en que fue tomado, puede haber sido el porcentaje de vehículos pesados, está por verse. Si uno saca las variables categóricas correspondientes a los sitios, tenemos esta otra regresión que dice, bueno, la mayoría, bueno, no es mucho lo que se puede explicar, el R cuadrado es solo ajustado, R cuadrado ajustado es solo de 23%, y influye en el peralte, influye el ángulo de deflexión, que tiene bastante sentido, influye la longitud de la clotoide de entrada. Esta estaba altamente relacionada con la longitud de la clotoide de salida y con el radio de curvatura. Y entonces tomó primero la longitud de la clotoide de entrada porque era la que más explicaba, y eso impidió que entraran después en la regresión el radio de curvatura y la clotoide de salida. Y pista, que es como decimos en Chile a los carriles, el número de carril también resultó significativo. Significa que los que van en los carriles más interiores, los que van en los carriles, no, perdón, los que van en los carriles más interiores pueden irse hacia el centro de curvatura todo lo que quieran mientras la berma lo permita. Pero el que está en la segunda pista no se puede ir hacia el centro de curvatura tanto que empiece a verse amenazado por el auto de la pista que tiene al lado, y así sucesivamente. Por lo tanto, hay un efecto de que a mayor número de pistas, menor wandering total. Esto es un trabajo en desarrollo, estamos todavía jugando con los datos, haciendo regresiones. Llama la atención la alta correlación de la variable dependiente con los sitios. 36% de la varianza se puede explicar por la elección del escenario. Una cosa que estamos explorando, pero todavía no hay mucho que mostrar, es usar, en vez de la longitud de la deflexión, de la transición, que está altamente correlacionada con el radio de curvatura, es usar el ángulo de deflexión de la transición. Que una cosa es la longitud de la deflexión, la longitud de la transición es igual al producto del radio de curvatura con el ángulo de deflexión, por lo tanto ahí debiera desaparecer en buena parte esa correlación. Otra idea que estamos trabajando es la visibilidad, sin resultados muy positivos hasta ahora, porque, entre otras cosas, porque la visibilidad es tremendamente difícil de medir, y la conclusión es, podemos hacerlo por apreciación experta. Hicimos un primer intento, pero también está altamente correlacionado, como resulta natural, con el radio de curvatura. Estos caminos de montaña, que son los que tenían los radios de curvatura menores, también están más restringidos, si cabe, que la Panamericana, para las posibilidades que dan de visibilidad. De hecho, es común que haya residencias al borde del camino con cerco o el mismo borde del cerro que no permite que haya un espacio para ver más de lejos. Y eso es lo que tenía para mostrar hoy día el Iván y todos. Muchas gracias.
Thank you very much, Rafael. So you have some minutes to discuss the ideas.
Yes, I do. Yes, I do.
Yeah, do you have more minutes, or Rafael? I know you have a class in a few minutes. Do you have more minutes for discussion?
I mean, I have like 10 minutes.
10 minutes? Okay. So someone would like to ask something for Rafael or Anna. I can see a discussion chat, but maybe Anna, it's nice to discuss again, just to record for the video, you know. So
Yeah, I think that could be, if it's no questions for Rafael, we can dive into the chat, but then since Rafael might be leaving soon, I think I will give him the chance to answer questions now. So maybe, yeah, if it's raising some question, burning question for Rafael, we go ahead with that piece. And then,
Or you can go ahead. You can go ahead, Anna, and let's wait if any questions to me appear in the chat. And
okay.
Actually, I have a question for
Rafael. For you as well. Yeah, maybe Jose, you can do that first.
Yeah. My point is, it's hard to get data from curves, especially in highway environments. So do you think it's a good idea to use this data, for example, to implement some models in traffic simulators? Have you ever thought about this topic to research or not?
Yes, my graduate thesis was about two-dimensional traffic model, microscopic traffic model. So it naturally connects with modeling. This research connects naturally with modeling. In fact, an effort I'm currently doing is trying to get to a causal model to explain why these variables are the ones influencing the lateral wandering. But I haven't had any success yet. I'm still trying. And that's it.
Yeah. And your question, Anna?
No, I think that then I will switch to Spanish here for our convenience. Rafael, no, muchas gracias por la presentación y esto. Me recuerda eso cuando yo empecé con la tesis de grado, bueno, de maestría aquí en España también hacía curvas, visibilidad en las curvas y cómo es la coordinación entre planta y alzado. Y por ahí va mi pregunta, ¿no? La parte de visibilidad creo que es uno de los factores que quizá puede ser el que te dé las diferencias entre los diferentes sitios que tienes. Y a lo mejor la visibilidad es muy complicada de calcular, por eso necesitarías quizá un modelo 3D, si la quieres hacer teniendo en cuenta la coordinación de la planta y el alzado, pero también podéis utilizar el despeje como proxy. Bueno, al menos en España lo llamamos despeje, que es la distancia que hay clara, o el clearance distance sería. Entonces, la distancia que hay entre el final del carril y el siguiente objeto donde puedes mirar. ¿Cuál sería ese máximo despeje? Te puede dar un proxy para visibilidad, que ese sería más fácil de calcular quizá que en verdad todo el perfil de visibilidad.
Claro, muchas gracias, porque de hecho es un problema que no tengo resuelto, que lo hemos conversado con Tomás, él es el experto en geometría y en diseño geométrico, y yo me dedico más a los modelos de tráfico y a la extracción de trayectorias y esas cosas. Y efectivamente probamos con una apreciación experta que en parte tenía en cuenta la clearance, y pero claro, de nuevo, el vehículo que va en la pista más externa tiene todo el clearance
Tiene
perdón,
mayor.
el carril más externo tiene todo el clearance de los otros carriles, y hay un tema, por ejemplo, hay una curva que tiene un clearance grande en la segunda mitad de la curva, pero si uno mira desde la primera mitad no ve clearance. Entonces, eso es una cosa que hasta ahora nos ha resultado difícil de agarrar. Tuvimos una primera aproximación, así más bien apreciativa, basada en el clearance, y en mirar la misma maqueta. No sé si lo expliqué bien, pero tenemos las maquetas 3D reconstruidas desde fotos de todos los sitios. Eh, y sí, algo contribuyó al R cuadrado, pero de todas maneras no era la visibilidad no era la variable más significativa, y seguían apareciendo los sitios como, cambiaba un poco el orden, pero seguían apareciendo los sitios como variables significativas.
Sí, yo creo que tanto la visibilidad como la longitud de la recta anterior también puede ser un factor. Si tienes un terreno que es muy curvilíneo, también
De
las
hecho,
personas ya pueden
ese-
ir, o sea, la parte de consistencia del diseño, como es de la consistencia del segmento, no solo de la curva en particular. Pero bueno, ya, no quiero acaparar. Pasamos.
gracias.
There's a question chat from Helica, and Juan raised your hand, so maybe Juan can ask your question.
Gracias, Elivan. ¿Se escucha?
Sí.
Yes.
Perfecto. Me demoré, no podía encontrar dónde levantar la mano, pero bueno, ya lo encontré. Oye, gracias Rafael por la presentación, gracias también Ana. Lamentablemente llegué tarde, no me pude conectar antes, así que me perdí mucha parte de tu presentación, Ana. ¿Ya? Rafa, yo tengo unas preguntas que son súper cortas en realidad, que tienen que ver con primero si dentro de los datos habían camiones o vehículos pesados en tu base de datos, si los separaste o no los separaste, porque ahí sin duda debe haber una diferencia importante. Te lo voy a hacer todo y después tú me comentas ahí brevemente, por favor. Vi que también tenías dentro de las variables independientes la velocidad, me pareció ver, o algo relativo a la velocidad. ¿Cuál era?
Sí.
¿Cómo la calculabas? ¿Era la velocidad promedio en toda la curva, la velocidad de ingreso a la curva? ¿Cómo la definía? Y después si la variable
Eh,
dependiente,
sí.
déjame terminar y ahí te doy espacio, son súper
Ya,
cortos.
no.
Y después la variable dependiente, wandering, ¿tiene valores positivos o puede tener valores negativos también? ¿Y cómo,
¿Eso?
porque eso te ayudó a explicar un poquitito, por ejemplo, el valor de las constantes que tú veías de los sitios, porque eran esos valores positivos, quiere decir que es positivo con respecto a una referencia. Alguno de
La
tus sitios no
constante.
tenía una variable dummy,
Sí,
en este caso me imagino.
sí.
Por lo tanto,
No,
todas son en relación a
perdón,
esa. Ya, sí, ya
ya.
sé. Ya, ahora ya ahí dejo para que tú puedas contestar, Rafa. Disculpa.
Ok. Sí, hay vehículos pesados, sobre todo uno de los caminos de montaña, el del Toyo, eran prácticamente solo caminos, solo camiones, porque hay una mina más allá. La ribera sur del río Maipo, por si alguien se ubica. Eh, y no lo hemos distinguido. No lo hemos distinguido porque, en fin, como digo, es un work in progress, y concentré el esfuerzo en otras cosas primero. Eh, la velocidad como variable independiente es la velocidad media temporal del vehículo en estudio, de la trayectoria que se está observando.
Perdón, para entender
Como
bien,
está
entonces
altamente
es
relacionada al radio de
la
curvatura,
distancia que recorrió dividida por el tiempo que se demoró.
sí,
Ya.
como la velocidad está altamente relacionada al radio de curvatura, no aparecía mucho en las regresiones, y también entonces finalmente lo que hicimos fue calcular una velocidad relativa, la velocidad de este vehículo respecto al promedio de los vehículos de este conjunto. De manera que ahí se fueran, con la esperanza de que ahí se fueran los efectos del sitio y los efectos del radio de curvatura. También hay unos resultados ligeramente distintos, pero no eran tan distintos como para que valiera la pena mostrarlos en esta presentación. Y el lateral wandering podría ser negativo en la eventualidad de que un auto pasara durante el arco circular de la curva más afuera de lo que estaba en las curvas de transición, que sería raro, pero no imposible. En general son positivos. y entonces es medido cuánto se fue un vehículo en específico hacia el centro de curvatura durante el arco circular.
Muchas gracias.
Rafael, there's a last question for you, if you have time. A question from Angélica. Sorry for my Spanish. ¿Fueron todos los vídeos a la misma hora del día? ¿Consideraron que los conductores podrían estar de frente al sol?
Sí, efectivamente. Lo iba a mencionar y no fueron todos a la misma hora del día. De hecho, hay uno que no lo mostré, pero que en el video se nota cómo los vehículos proyectan unas sombras bastante largas porque fue cerca de la puesta de sol y efectivamente es un punto que yo creo que no he tomado nota de revisarlo nunca, se me había ocurrido, pero qué bueno que me lo pregunten aquí porque es digno de ser revisado, sí. De todas maneras, todos fueron con luz de día, en días con buen clima, entonces no hay una influencia de la lluvia, ni de la neblina, ni de ninguno de esos otros factores.
Okay, thank you very much. Ana, there are 3 questions on chat. I know you answered
Perdón,
before.
yo me despido. Muchas gracias a todos y que estén bien.
Thank you very much,
Gracias.
Rafael. See you. So, Ana, I know you answered before, but if you let me answer again, you can comment in a few minutes, please. The first one is from Angélica. ¿Podrías, por favor, explicar por qué de los 1.650 selecionados en la muestra, solo 982 tiveram respostas completas?
Sí, no, aquí la encuesta, como he comentado en el chat, la encuesta tenía 12 páginas. Al final en Internet no suena tanto, cuando son en escrito son menos de las 12 páginas, pero sí que tenía 12 ventanas que la gente iba avanzando en la encuesta. Y entonces 1.600 empezaron la encuesta en la primera página, pero vimos que conforme avanzaban, algunas continuaban y otros abandonaron la encuesta. La mayoría de los que abandonaron fue cuando llegaron a las choice tasks. Entonces, de ellos no tenemos las sociodemographics, eso estaba todo al final, y luego también sus hábitos de cómo van en bicicleta también estaban al final. Eso se perdió. Y entonces esas respuestas incompletas no las tuvimos en cuenta en el análisis. Y luego también dentro de esa encuesta, aunque estaba dirigida a Estados Unidos, también tuvimos algunas respuestas de otros países. Entonces había respuestas de Canadá, también había respuestas de Alemania y consideramos que las imágenes que se mostraban no eran significativas para ellos. Entonces esas respuestas no se tuvieron en cuenta. Eso explica. Igualmente es un 60% completo la encuesta, que en este tipo de encuestas es un porcentaje elevado, diría yo. Suele ser más personas lo abandonan.
Okay, makes sense. The other question is from Victor. Perception stress in this context depends also on the characteristics, experiences, and expectations of the individuals. Did you consider including the effect of social economic characteristics like age, sex, income? Also, the effect of risk perceptions, pro-environment attitudes, or willingness to do sport, lightened variables. Another question is related to the composition of the traffic. Is there, if there is a high presence of heavy vehicles, it may impact the level of stress. It's a comment.
Yeah, I think that's a good question. And then here I'm going to show, let me see if I can find it. And I totally agree. So it's not only what I mentioned here was the level of confidence, because that's the main assumption that we were going to see, is that the previous studies were using this level of confidence as the main predictor to say this is a confident user, this is a less confident user, and we're targeting the opinion of the most confident users for the case of rural highways. So that's why in this presentation, we put the focus on the level of confidence, but in fact, we have also all the other sociodemographics from the people, and then we can do the same analysis segmentation by other sociodemographics. I didn't show this here on the presentation today, but in a previous study or an analysis, when we didn't use the individual distribution of the betas, we used the sociodemographics as another independent variable of the sample, and we actually found differences on the perceptions based on sociodemographics. The most important factors were gender, so females had a lower propensity to cycle compared to a male. Given the same conditions of everything, females usually tend to respond less times I will cycle in these conditions. And then also age was a significant variable, especially the older population segment was more prone to cycle compared to the others. And this could be a proxy of experience. And here could be a lot of also other correlations that were not seen in our sample, but we can think that also the older population here might be in more experienced in this type of roads and therefore more confident. Although in our multi-correlation analysis, we didn't found a specific correlation with the age and also the stated confidence level of the people. But those two were the ones who were more significant in our sample. And I pull in here also the other one, but yeah, cyclist type, age, and gender were the most significant. We also had cyclist habits, but those were not significant in our sample. So I totally agree the piece of sociodemographics is important and it was considered. Unfortunately, we were not including latent variables, so we didn't have attitudinal variables on the questionnaire, but I feel that this is also something important. So if someone is pro-environment or it's also anti-car, they may have a different perception than others, but it was not included, unfortunately, in our questionnaire. And the willingness to do a sport, we do have the uses for cycling on rural highways, so we asked for the purposes. We did not analyze that variable. So I think that it will be quite interesting to see the people were answering a sport, leisure, recreation on those, if they will have a different effect. We controlled for the fact if they were cycling on rural highways for leisure. So that was a specific question, but it was not significant in our sample. And the last piece with the composition of traffic, I totally agree. The presence of heavy vehicle may impact the level of stress. In fact, when we were looking at the highway capacity manual, the presence of heavy vehicles is one of the driving factors for the level of service, but also it was calculated for the urban areas. I would say that the effect in the case of rural areas will be even higher because the speed differentials are even higher, and with the dimension of a truck that is passing next to a bicycle, the dynamic forces will be quite strong. And but we didn't include it in our survey, unfortunately, as well, because we needed to limit the number of attributes, and that was lower rank in our practitioner survey.
Okay, the last question is from Ivan. Transferring bikeability indexes to other contexts could be problematic because of the diversity in socioeconomics, user preference, and perceptions of built environment characteristics, which justifies the construction of local index. What about the transferability of these models to the latent context? In other contexts, which other factors could be taken into account?
Yeah, and I think that Ivan raised a really good point. And then here will be in this piece of the transferability. I think that the results are not directly transferable to any other country, or even some regions from the US could not be transferred these results. They might be in Florida, may have a different opinion that you were talking with Hawaii. So I think that even in the same country was the US would not be directly transferable. Still, our sample was not geographically biased, so still we consider that we have countrywide results, but it's true that the images that they were shown were more to the East Coast and not the West Coast, and then people from the West Coast might feel that those did not represent that well the conditions that they actually see. What I think that is really is transferable in the other one will be the methodology. So still we can use similar methodology and then similar framework that instead of having this bias with the a systematic bias when we have a self-stated level of confidence, but using the entire distribution. I think that that's the key factor. And then I think that that's transferable to any country, given that they have a similar survey stated. To create the surveys, I feel like the top attributes would be set the same in all the countries. So still the presence of the shoulder and the width of the shoulder, speeds and traffic volumes would be the top attributes to be in all of the surveys. Probably in other contexts, if it's a flat country, the terrain will not play a role, and then that could be changed by the heavy vehicle conditions or the lane width as well. We didn't play with lane width of the automobile lane width. That could also be a factor that they should be adapted to the local context. But I think the top three will be for sure maintained, and pavement conditions as well. And I think that this is here something to be considering as well would be the pictures, that also the pictures should be adapted to the local context. So not showing a US picture to someone in Germany, they will say this is not our conditions here. Usually shoulders are non-existent. So it's something that it has to be adapted to each context, but I think that the methodology is robust and can provide a framework for further developing this level of traffic stress criteria.
Okay. I think you don't have more questions, so I'd like to say thank you again, Ana, for the presentation, for the answers. And you can finish this webinar, and I'd like to say thank you for the audience, and also for Juan, Angelica, everyone that organized this webinar. Okay, thank you very much, guys. Have a wonderful day and a wonderful week. Okay.
Gracias a todos
Thank
por
you.
este muy buen webinar. Gracias a Ana, Juan Carlos, Elievan, y esperamos a todos en el próximo mes con otro webinar muy interesante. Gracias. Adiós.
Gracias.
Muchas gracias.
Gracias.
Que estén muy
Hasta
bien.
luego.
Chao, chao.
Adiós.
Thank you.